In this segment, I want to dive into rotational motion. And so in Chapter 6, we're going to kind of cover three basic topics. We're going to cover basics of rotational motion. And once we've got that set up, then we're going to talk about rotational motion, forces applied to rotational motion. So first off, just what is rotational motion? How do we describe it? Secondly, applying force problems So applying Newton's second law to force problems in rotational motion. And then thirdly, we're going to talk a little bit about gravity and how it works, which is one of my favorite things to talk about. So lots of interesting stuff in this chapter. The first thing we need to talk about is just rotational motion. And we need to figure out a system for describing rotational motion. And so, let's imagine here that I have a ball on the end of a string and I'm winging it around my head. Or alternatively, I've got this bike tire here, and we could think about, say, that blue piece of tape that I have hooked onto there. Okay, so we've got a ball on the end of a string swung in a constant speed in a horizontal circle. So we could also visualize this as this piece of blue tape that I have rotating in a horizontal circle. Is it accelerating? What do you think? I hope that you think it is. Because it is accelerating, yes. The direction of its velocity is changing, right? So thinking about this blue piece of tape, right? Over here it's headed in this direction, but over here it is headed in this direction. So its velocity has changed. The direction of its motion has changed. What do we call that acceleration? The centripetal acceleration. Recall that centripetal means center-seeking. So this is the center-seeking or centripetal acceleration. In what direction does the centripetal acceleration point? It points towards the center of the circle. Okay, so that was a bunch of review questions. Here's a quick clicker question. When the ball reaches the break in the circle, which path will it follow? Well, let's imagine that this is a top view of a ball rolling in some track. Okay, so this is a top view, the ball is rolling in some track, and then when it reaches, it's going this way, and then when it reaches this point in where the track is broken, what's it going to do? Pause the video. I'll see you on the other side. Okay, so I guess the point is Newton's first law, right? What does Newton's first law tell us? Newton's first law tells us that any object that is in motion will continue to move in a straight line at a constant speed. Any object that is at rest will remain at rest unless there is some net force acting on that object. Now, if we imagine this ball in the track, there must be some force keeping it on the track, right? There must be some force causing it to move in a circular motion. What is that force? Well, it must be some kind of a normal force, some sort of a force exerted by this track. And as long as it's in the track, that force is present and can keep it moving in a circle. But as soon as it reaches this break, is that force still there? It's not, right? So the force that was making it move in a circle is gone. What will the object do? It will move in a straight line and at a constant speed, in accordance with Newton's first law. Okay, so again, recall that acceleration is called the centripetal acceleration. Recall that if velocity and acceleration are in the same direction, that object is speeding up. If velocity and acceleration are in opposite directions, that object is slowing down. And if velocity and acceleration are perpendicular, then that object is turning a corner. So recall that the centripetal acceleration always points to the center of the circle, and it makes a right angle with the velocity if this is moving at a constant speed, and the only change in its velocity is turning a corner. So that is our centripetal acceleration, and recall that it can be written as v squared over r. We're going to introduce a new symbol in this chapter, omega. So while we can write it as v squared over r, we can also write it as omega squared r. And so this omega, we call this omega as the angular velocity. And so it's how fast something is rotating. And so, if you've looked at your tachometer in your car, it says how many RPMs your engine is rotating at. Essentially, that is an angular velocity, right? And so here I have this wheel again, right? And I've got that piece of blue tape and the piece of green tape. And looking at this, the green tape and the green tape and the blue tape, they both go around. You know, every time the green tape goes around, the blue tape also goes around. Vice versa, every time the blue tape goes around, the green tape also goes around. So these two pieces of tape have the same angular velocity. It describes how quickly they are rotating. Now, our standard unit is radians per second. And so I want to take just a minute and talk about the unit of the radian. It's sort of a goofy unit. I know the first time that I came across the radian as a unit, I thought it was really silly, right? You know, dividing a complete circle into 360 pieces, 360 is sort of a strange number. Turns out, though, there's a good reason for it. These ancient numbers, you'll often see 60 a lot. A dozen is a common ancient number. 360 is simply 6 60s. And so we see these numbers historically because in a pre-calculator era, even more so, not just a pre-calculator era, in an era where people were not doing math on paper, in a pre-written algebra era, in an era where people did all the math they had to do in their heads, base 10 is not important, right? Base 10 is super handy with the invention of the decimal system. But if you think about pre-invention of the decimal system, when people were doing math in their heads, what numbers would you want to work with? You'd want to work with numbers that were divisible by a large, large number of different numbers. So for example, 60, it's hard to do 60 multiplication in your head and my head as modern humans. We're so used to our calculator and our base 10. If you think about 60, right, it's a little bit hard to do mental math with 60 for you and I probably because we're so used to base 10 and we're so used to writing numbers in base 10 and we're so used to the decimal system, right? But if you think about 60, it's divisible by 1, 2, 3, 4, 5, 6, not 7 or 8 or 9, but it is divisible by 10, also 12, also 15, also 20, also 30, right? So there's a whole bunch of numbers that divide evenly into 60, which would probably be really convenient if you were doing math in your head and you had no way of writing these things down. Anyway, sidetrack. Dividing a circle into 360 pieces seems a little strange. Again, I think there's a reason for it. Dividing a complete circle into 2 pi radians? What? How does that even make sense? Right? Like pi is not even a rational number. Right? You can't even write pi down with a pencil because it's got an infinite number of decimal places. So how am I going to divide a circle into 3.14159 equal pieces? What? That doesn't even make any sense. It does make sense. It does make sense. There's a really, really good reason for using radians. And it comes from a well-known equation. Right? If I have a circle and I know the radius, then how far is it around the outside of that circle? The circumference is 2 pi times the radius. So in this case, the circumference equals 2 pi r. Okay, great. So in other words, how far around the entire circle is it? Well, 2 pi times r. Great. Well, what if we cut this circle in half instead? So here's half a circle. Same circle, same radius. But now I want to know what is sort of this distance here. The distance around the outside of my circle. Let's call that c 1/2. Well, it would be 1/2 of this, right? So if all the way around is 2 pi r, then halfway around must just be pi r. And what if I just had like a little quarter of a circle, like a little pie shape here? And I just wanted to know how far it was here. Well, what's that? Let's call that c 1/4. Well, it would be 1/4 of this, or 1/2 of this. Or how about pi over 2 times r? Aha. So somebody who is smarter than I am had this great idea. And they said, hey, let's define this angle here. Let's define that angle. And, you know, it could work for even any old wedge shape. It doesn't have to be a quarter or a half or a full. If this is r and I just want to know how far this is over here, and I don't know, let's just call this s. So if I just want to know how long this arc here is, then what we can do is if we invent a new unit for measuring angles, and we say, well, all the way around is 2 pi of these units, halfway around is pi of these units, a quarter of the way around is pi over 2 of these units, then we can write this relationship very easily, where S equals theta times R. And this works now for any angle, not just these special ones, but any angle as long as theta is measured in radians. Okay, so as long as we say, okay, well, 2 pi radians equals 360 degrees, then we get this nice relationship between the distance along an arc here and the radius and the angle. It's a very convenient relationship, and that's why we use radians. They seem like sort of a strange unit the first time you come across them, but there really is a good reason for them. Okay, so again, angular velocity says how fast something's rotating, and our standard units are radians per second. And so be a little bit careful and remember that 2 pi radians equals 360 degrees. Radians are a little bit goofy too. We just came up with this equation, right? S equals R times theta. What are the units of S? Well, S is some length, so meters, centimeters, something like that. R, what are the units of R? Again, it's a length, so its units are meters, centimeters, something like that. Then what about theta? Theta, radians are really unitless. Which is a little bit strange, but they have to be. If you think about the way we defined them, they just have to be. Okay, so our standard unit is radians per second. We could use degrees per hour or revolutions per minute. This is a common one in everyday life. The tachometer on your car probably measures things in RPMs. And for right now, we're going to constrain ourselves to uniform rotational motion. In other words, we're talking about rotational motion where the rate of rotation is constant, approximately this. We're not talking about this scenario from here to here when I am speeding it up, right? So that would be accelerated rotational motion, and that's not what we're talking about right now. What we're talking about right now is constant or uniform rotational motion. In other words, things are rotating at a constant rate. And so, if we're talking about constant rotational motion, then we will use this idea of average angular velocity quite a lot. Omega is the change in theta over the change in time. And I will just remind you that for velocity, that was a change in position over a change in time. And so you see here that our linear velocity is defined very similarly to our angular velocity. This is how far in a circle over the change in time. This is how far in a straight line over the change in time. Okay. We can relate these things with this equation. So if we wanted to know the tangential velocity, then we could just multiply the angular velocity by the radius. Now notice that this equation here in green on my PowerPoint, it comes straight out of this equation right here, right? For those of you that have had some calculus, if you took a derivative of both sides, we would end up with V equals R times omega. So, in other words, this green equation on the PowerPoint here, this has to be in radians per second for this to work. Omega has to be in radians per second for it to work. So I've said, sometimes you can use RPMs or something like that, degrees per second even. That's not as common, but you could do that. But if you're going to use this equation, you can't. If you're going to use this equation, you absolutely have to use radians per second here, which will get you a velocity. Okay, got a couple questions to kind of practice thinking about this. Here we have a record. It is a Beatles record, because why not? And specifically, it is the Magical Mystery Tour, possibly my favorite of the Beatles records. And it is a spinning. And as luck would have it, 2 Beatles are standing on this record. So, here's my question for you. Which Beatle has the greater angular speed? Beatle A or Beatle B? Well, angular speed, let's see, angular speed, that's the rate of rotation. That's how many radians per second they're going. We could also express it in RPM, right? And if the record is turning at 33 1/3 RPM, that means that every minute it goes around 33 1/3 times. That means that this little part where it says stereo, that goes around 33 1/3 times in a minute. It means beetle A goes around 33 1/3 times in a minute, and it means beetle B goes around 33 1/3 times every minute. That means they both have the same angular speed. They have the same angular speed. But which beetle has the greater linear speed or tangential speed? Which beetle feels more wind in their hair? Well, pause the video. I'll see you on the other side. Looking at this equation, V equals omega times R, they both have the same omega, which means the greatest R has the greatest speed. Bug B is just going faster. So even though bug A and bug B complete the same number of revolutions every minute, bug B goes farther every time he does do a revolution. I said he. I don't actually know the gender of that beetle. Okay, here are some definitions. We use capital T for the period. The period is the amount of time for one complete revolution. Since it is an amount of time, we use units of seconds. Frequency is the number of rotations in 1 second. So you can see that frequency and period, they both tell us basically how quickly something is rotating. But they kind of tell they're inverses of each other, right? So period would be like seconds per revolution, and frequency would be like revolutions per second. You can see that they're just upside down from each other. Now, we do have to be a little bit careful. We use frequency to represent the number of rotations in 1 second, which is F. And we use omega to represent the angular frequency, or the number of radians per second. So omega is radians per second. Frequency is revolutions per second. But notice they tell us the same thing. They tell us how quickly the object is rotating. Since one revolution is 2 pi radians, omega is 2 pi times F. Similarly, we can write it as 2 pi over T. Let's do a real quick example. A hard drive disk rotates at 7,200 RPM. The disk has a diameter of 13 centimeters. What are the acceleration, speed, and angular speed at the edge of the disk? And how do these values compare to the acceleration, speed, and angular speed at a point that is halfway between the center and the edge of the disk? All right, I want you to think about how to start this. I will erase my board. Okay, I think the first thing we should do is, we've been given this rotating rate, this rate of rotation in 7,200 RPMs, revolutions per minute. I think we better convert that to radians per second so that we can use that equation that I gave a couple slides ago. So we have 7,200 revolutions per minute. We'll just do a quick unit conversion here. 2 pi radians in 1 revolution. And of course, 1 minute is 60 seconds. My revolutions cancel, my minutes cancel, and I should have an answer in radians per second. 2 pi is about 6. 60 seconds, 6 or 6. We should be dividing this by about 10, right? Just, it's good to have an idea of what you're shooting for before you even run your calculator. So when I do run my calculator, I get 754 radians per second is omega. And again, it's a little bit, pretty close to a tenth, a little bit more than a tenth. That's fine. Looks good. Okay, what are the acceleration, speed, and angular speed at the edge of the disk? Well, what did I just find? I just found the angular speed. So here we go. There's the angular speed at the edge of the disk. How about the acceleration? Well, we could use the acceleration. The centripetal acceleration is omega squared times r. So that's 700. And I do apologize. I had a backwards moment here. I wrote 745. It should be 754. I apologize. Okay, moving on. We have 754 radians per second squared times r. They told us that the diameter was 13 centimeters. That means the radius is half of that, or 6.5 centimeters, also known as 0.065 meters. When I run my calculator, I get 3,700. Meters per second squared. Okay? Notice that it's the units are meters per second squared. Right? Centripetal acceleration, it's kind of a fancy acceleration because it's the turning a corner kind of acceleration, but it's still just an acceleration. It's still a change in velocity over a change in time. So it has the same exact units, right? So this is just meters per second squared. It's not any different units. It's just the same. Okay. Moving on. How about its angular speed? Oh, we found its angular speed. Its regular old linear speed. And we'll use v equals omega times r. And I guess this is a point maybe I should emphasize here, is that if I mean angular speed, I will say angular speed. So if I just say, what's its speed? Well, then you know that just means it's linear speed. And specifically, it means it's instantaneous linear speed, doesn't it? It doesn't mean like average, right? So if I just say speed, it means instantaneous linear speed. If I say angular speed, it means it's angular speed. Okay, so omega is 754 radians per second squared times r, 0.065 meters, and we get a number which is 49 meters per second. Okay. Not too bad. Another note on this. This is a huge acceleration, isn't it? But it's also a very tiny little hard disk, and it doesn't have a lot of mass, right? So if we imagine just a little chunk on the side, it's not going to weigh very much. So it's not going to require a ton of force. However, folks have done experiments, and they just see how fast they can get these things rotating before they fly apart. And it's faster than this. So anyhow, this is a large number, but it's reasonable. Okay, how do these values compare to a point halfway between the center and the edge? Well, let's see. Let's look at the acceleration first. Actually, let's look at omega first. So omega at the halfway point is exactly the same as omega at the edge. Why? Well, they're both describing, well, the omega is the angular velocity. How fast is it rotating? Well, the edge is rotating at the exact same rate as a point halfway, right? Both the point halfway and the point on the edge, they both go around 7,200 times every minute. So those are exactly the same. How about the acceleration? Well, the acceleration is proportional to omega squared. That doesn't change. It's also proportional to r. So if we have half the r, don't we have half the centripetal acceleration? And so we should then go ahead and write that a 1/2 is equal to 1/2 of a at the edge. Similarly, the linear velocity is proportional to omega, which doesn't change, and to r. Half the r means that v at the halfway point is equal to 1/2 v at the edge. Okay. So, there we go. Here is my angular velocity, my centripetal acceleration, and my linear velocity on the edge. And at the halfway point, the angular velocities are the same. The centripetal acceleration is 1/2, and the velocity is also 1/2.